Today, tomorrow, and at least Monday, and maybe Tuesday, we're going to be working on projectile motion. The actual content is broken into two pieces. One piece we will cover today. Yep. One piece we will cover today. The second part we will cover tomorrow, but my feeling is that we almost always need to spend a second day on the stuff for tomorrow. So part two we will learn tomorrow, but then probably on Monday we will practice more. And then on Tuesday we were going to be doing a lab dealing with projectile motion. And then Wednesday and Thursday of next week, the way I've got things planned is review, and Friday of next week would be your kinematics exam. Okay? And it's a big exam. It covers a lot of material. When you compare your exams in physics to math we have like typically 7 units. The whole semester broken into 7 chunks. Physics we have 4. So the unit exams are quite extensive. They cover a lot of material. What we're dealing with here is solving problems involving projectiles that are launched horizontally. So, for example, as an illustration, this is a type of problem that we should be able to solve at the end of today. If I roll a small toy car off of a table at 4 meters per second, where is it going to land? That's what this question is going to ask us. I mean, will it land 1 meter away from the table? Will it land 5 meters away from the table? And I hope you understand that the faster the car is moving, the further away from the base of the table it's going to land, right? Do you agree that if it were moving off the table at like 1/10 of a meter per second, it's just going to hit the ground, but if it were moving faster, it's going to land further away? All right, so those are the types of problems we're dealing with today. And, you know, honestly, looking at the clock, I don't know. There's a demonstration here in this lesson. I don't know that we'll get to the demonstration today. We may get to it tomorrow. Okay. So remember from yesterday that for objects trying to move in a particular direction, notice I say trying to move in a particular direction. So a boat points north. It tries to move north, but because the river is flowing maybe west, it's not successful in moving north. Remember that when you have an object that's attempting to move in a particular direction, but there is a perpendicular influence like the wind for a plane or the river for a boat, then each component of the motion acts independently of the other. Now I am recording this, so I'll post a link to the video later today in our Google Classroom. What I'm going to show you, don't attempt to write down. It's quite extensive, but you can watch this portion of the video if you like. This was the illustration that we talked about yesterday, I believe, where we had a boat which was steering north. It's pointing north, and it's going to be moving north at 4 meters per second, but the river is flowing west at 3 meters per second. We've learned that that bluish vector is what really happens, right? It actually moves at a particular angle at 5 meters per second. And again, I didn't draw my horizontal first like I've trained you to do, only because it looks better up here. My point is going to be clearer by drawing the vertical first. So what this means is that every second that elapses, the boat will be 4 meters closer to the shore. And every second that elapses, the boat is going to be 3 meters further downstream. Right? And I'm not saying the boat moves north 4 meters, stops, moves west 3 meters, and then north 4 and west 3. It's happening seamlessly at the same time. So after 1 second, if the boat starts here where you see the boat, after 1 second, the tip of the boat is in that position. The tip of the boat will have moved forward 4 meters, and it will have moved to the right 3 meters. And during the next second, it will continue to do that. It will move north 4 meters, west 3, north 4, west 3, etc., etc., etc. And again, you understand this is just a time-lapse thing. The boat moves seamlessly. It's not appearing some distance away. What's really important about this is the following. Regardless of how fast the river flows, if the engine speed is 4 meters per second, the boat is going to move 4 meters per second north every second. It's going to move 4 meters every second north if it points north. Regardless of how fast, so it doesn't matter how fast the river is flowing here. If the boat points north, it's going to move 4 meters per second north every second. Regardless of what the captain does, maybe the engine shuts off. Maybe the captain of the boat throttles at a higher speed. If the river is flowing west at 3 meters per second, then every second that goes by, the boat's going to be 3 meters further along. And those two things are independent of each other. This is tricky. They happen at the same time, but they don't determine each other. What determines how far closer to the shore you get is the engine speed, and what determines how far downstream you go is the river speed, or velocity, I should say. So horizontal, this is the most important part so far. Horizontal and vertical components of motion are always independent of each other. So we have a warm-up now. And at first glance, this looks like a question from yesterday. We have a river that is 80 meters wide, and it's flowing east at 8 meters per second. What does that mean? It means that this is the river that's flowing east at 8 meters per second. All right? There's a huge, huge difference, though, because it says a boat launches itself from the north shore pointing south. So the boat is going to be moving from here south. The difference is this. The boat is not going to be traveling at a constant speed. The boat is going to accelerate uniformly at 10 meters per second squared. But it does start from rest, which means the initial velocity of the boat is 0. But it's accelerating. It's accelerating at 10 meters per second squared. So a short time after we start this process, it's going to be moving fast. Then it's going to be moving faster. Then it's going to be moving faster. And it's going to continue to accelerate vertically. But what's really important is, since the river is flowing at 8 meters per second east, it's always going to be moving at 8 meters per second east. Is it always going to be moving at a constant speed south? No. That speed is going to be increasing. And I've got a table here that I would like us to complete. Let's start with the motion east. Don't forget, this is 8 meters per second east. Well, what is the velocity 1 second after the boat leaves the shore? 8. What is the velocity 2 seconds after, 3 seconds after? It's always 8. Who can tell me what kind, another important thing, who can tell me what kind of motion this is in that first table?
Uniform.
It's uniform motion. The river is flowing east with uniform motion. Now well, let's do the displacement. I don't think we need a calculator for this. After 1 second moving at 8 meters per second, you will move 8 meters. After the second you will have moved a total of 16. Every second that goes by, you're 8 meters further east in the river. So these will keep going up by 8. Does your table go up to 6 seconds, by the way? Okay, thank you. This is uniform motion. Okay. Now, we don't really, you understand that we could have used the formula here, and the formula would have been that to find these displacements. Okay. My question is this, and please don't write this down. Why can I not use that formula to populate the second table? Joseph?
Because the speed accelerates or the velocity?
Right. It's not uniform motion. It's accelerated motion. And this formula doesn't work. Speed equals distance over time is used for uniform motion. What do we use for accelerated motion? Well, let's write down first of all that this is accelerated motion. what do we use for accelerated motion? We use those 5 kinematics formulas. A equals VF minus VI over T, VF squared equals VI squared plus 2AD. I'm not going to recite them all. Those 5 kinematics formulas. So how would we find this velocity after 1 second? I want to just go to a different screen right now. We're talking about the second chart. We can find the final velocity in the vertical direction by using this formula from our formula sheet. But notice I've slapped some more labels on that formula because this accelerated motion is occurring vertically. When I talk about A, it's the vertical acceleration. When I talk about VF, it's the final vertical velocity. VI is the final initial vertical velocity. The boat starts from rest. It's at the very beginning, it has no speed vertically. And that means this formula becomes and if I were to put in, say, for example, 10 meters per second squared, this is south, but the velocity will be south, so I'm not worried about the direction. Do you agree if I put in 1 second, you're going to get 10 meters per second? If I put in 2 seconds, you're going to get 20 meters per second? Okay, this is why I chose 10. The true understanding of acceleration is that if the acceleration is 10 meters per second squared, and that happens to be south, that means the velocity increases by 10 meters per second south every second. You might wonder why I'm using south. That reason will become apparent in a bit. So after 1 second, this will be 10, then it will be 20, then it will be 30, then it will be 40, then it will be 50. And after 6 seconds, because of this rocket-propelled boat, it's going to be traveling 60 meters per second. Okay. How do we find the distance? Well, we can use this. Whoops. We can use, and for the benefit of everybody, I don't want to leave anybody behind here. I'm talking about using this formula for accelerated motion. But since the initial velocity since it's vertical, then I do this, right? And since the initial velocity vertically is 0, that term is gone. I'm using d equals 1/2 at squared because the initial velocity is 0 and everything is in the y direction. So we need to calculate that. We need to take our calculator and go 1/2 times 10 times 1 squared, 1/2 times 10 times 2 squared, etc. And I'm going to put the numbers up here, and you're going to double check my work, okay? By the way, I'm just looking at the times. You could calculate the distances using these velocities, but I think it's easier to just go 1/2 at squared. My confidence level is very low on these. I don't know if my reasoning is right in my head with the math. Are those the numbers you're getting? Okay. So here's what I want to point out to you, and it will be very important for the next question, which is also part A, by the way. I know that. What happens is, if the boat is traveling at a constant speed like yesterday, In fact, I want to go back and just look at that. If a boat is traveling at a constant speed from yesterday, then it travels across the river equal distances regularly. And it travels down the river equal distances regularly. And the reason for that is the motion across the river is uniform motion, and the motion down the river is uniform motion. What is different here is that the river is moving the boat at a regular distance interval every second. The spacing of the motion horizontally will be regularly spaced, but the spacing of the motion vertically will be increasing spaces. So if we look at where the boat is after 1 second, it will be a certain distance across the river. But after a second, it will not be twice that distance, it will be even further. Are you with me on that? The really important thing here is this. Not sure why I have to do this all the time. The really important thing is the two types of motion. One of the types of motion is uniform motion, and one of the types of motion is uniformly accelerated motion. If they're both uniform, the boat travels in a straight line at an angle. What's going to happen here? So now we're at the second part A. I am aware that this is part A as well. Okay, I just have to renumber some things. It's not a big deal. Describe the path that the boat follows. Okay, well, here's the boat to begin with. The boat just pushes off of the shore and the engines are fired up. It's not moving vertically downward yet, but the river is already moving it to the east. That describes the vectors, velocity vectors that the boat is experiencing. 1 second later, the boat will be further downstream and it will be further away from the shore. Are you with me? And it will have a vertical velocity to it. It will still have a horizontal velocity. What can you tell me about these two velocities in the horizontal direction? They're equal, right? They're the same, because the river is not accelerating. The river is flowing at a constant speed. A short time later, it will also still be a certain distance downstream. It will still have this same horizontal velocity, who can tell me what you notice about these two vectors? Christina?
They're not the same. The second one is longer.
The second one is longer. Why?
Because it accelerates.
Right, because there's an acceleration vertically. I don't know how accurately I've done this, but if I've done a pristine job, what can you tell me about that distance and that distance? They're equal, right? Why are they equal? Because it's moving to the right at a constant speed. On the other hand, what can you tell me about those two distances? They're not equal. In the second of travel, the boat travels further south. So the end result is what happens is it curves. And the angle that it's moving at keeps getting more and more southy as time goes on, because that vertical component of its velocity keeps increasing. So horizontally, there's uniform motion. Vertically, there's uniform acceleration. If I said to you, how do you determine the actual velocity of the boat here? You would do the following. You would draw these tip to tail, wouldn't you? And draw the hypotenuse. Well, I just want to get this back to where it was. I'm not going to move them over and draw them tip to tail. I'm just going to point out that those would be the resultant velocities. And by the way, the initial resultant velocity would be this x component at the top. So what kind of path does it follow? We can finally answer the question. It's a curve, right? Does anybody know the mathematical name of this curve, though? It's a special mathematical term. No? It's a parabola. And you learn about parabolas in Math 20. This is called parabolic motion. And the reason why I've set this up, everybody, so that the object is moving east because of the river motion, and it's accelerating south. You remember that diagram I showed you with the car going off of the table? Because this is exactly what the car is going to do. Except it's not an engine, it's not a rocket pushing the car towards the surface of the earth. It's gravity. It's accelerating at not 10 meters per second squared, but 9.81 meters per second squared. I am just at a loss with this new bell schedule. Does anybody know what time this class goes till? 11:40? 10:40. Okay. So, describe the ball that the path actually follows. Thank you for that, Corey. It's a parabolic path. You know, we want to be sophisticated in Physics 20 and more sophisticated in saying it's some kind of curvy thing. There's a word for it. It's a parabola. How long does it take the boat to reach the South Shore? Well, are we told the width of the river? I think we were. Wasn't it 80 meters? Okay. And by the way, if it takes less than 6 seconds, don't worry about it. I just made the chart to explain my point. So this is 80 meters. Now, when the boat reaches the South Shore, it will have actually traveled a lot more than 80 meters. What do I need to add to this notation to tell me that a displacement is actually 80 meters here? There's something that I need to add. Why? This is a vertical displacement. So, do we care what the river is doing? No. Look, if we go back to this table, when we calculated, let me get back here, when we calculated, there we go, this 5 meters in the second table, and this 20 meters, and this 45 meters, did we ever make use of the 8 meters per second? No, it's got nothing to do with it. We treat the vertical motion independent of the horizontal. So all we're going to do, everybody, is a simple kinematics problem here, where, well, I can show it to you, where VI vertically is 0, A vertically is 10, and D vertically is 80. You'll notice I don't have Y's on these. Why don't I have Y's on them? Because it's in a heading that says south. If you wanted to, you could certainly do that, right? So if we want to find the time, then I guess we just have to go to a kinematics formula. I want to go back to what I've written because I'm more comfortable doing it this way. These are all south. And some of you might say, well, why aren't you using negative then? You'll get more used to this. If they're all south, we don't need a direction like positive or negative. Let's just, positive is south. VI is 0, and that's in the y dimension. So we want to find time. Displacement equals VIT plus a half AT squared. And again, you know, to be technically correct, I'm going to add y subscripts because these are all south. But if you don't want to add them, you don't have to. The fact that we are looking at south directions tells you it's all south. So we get D equals a half AT squared. We put in 80 meters. We put in 10 meters per second squared. And we solve that and get 4 seconds exactly? Can you work that out for me? It is. You have to multiply 80 by 2 and divide the result by 10, and then take the square root. I hope everybody understands we're getting a nice number without decimals, probably, well, in part because I've chosen an acceleration of exactly 10. And we happen to get 16 before we take the square root. Okay, so it takes 4 seconds for the boat to get across to the other side. The next question is, how far downstream will the boat be? Well, that is asking us to find a displacement. But that's not good enough. What should I add to my notation here so that I'm talking about distance downstream, Owen? X. I'm talking now about X. And horizontally speaking, it's not accelerated motion, it's uniform motion. The only formula you have really for uniform motion is this. If you want to impress your family and your pets, you can put vector symbols above everything. Maybe not your pets. You can put X's on the things that are directional, in other words, the things that have vectors. And was it 8 meters per second? Okay, so we can put in 8 meters per second. Again, I'm just leaving out the units here. Equals d x over 4, right? See, even though we treat horizontally and vertically, even though we treat the horizontal and vertical components of the motion separately, the simple fact of the matter is there are not two boats, right? It's not one boat doing one thing and the other boat doing the other. It's one boat that is moving east at 8 meters per second at the, listen, at the same time as it's moving south in accelerated motion. The time is the same. So if it was 4 seconds to cross the river, it's moving down the river at 4 seconds. And when we cross multiply here, you get a displacement of 32 meters east. Any questions with that example? Okay. We are going to skip over the question that's at the bottom of the page. That requires a demonstration, and I would like to show the demonstration to you in the hall and potentially even go up on the landing by the second floor elevator and do it from there. And if we do that, then we get back. We're not going to even have time to finish the next example, but we will have some time left. So I'm just going to do the next example. We're going to move on. We'll do the demonstration tomorrow. The whole idea here, everybody, and I think I've covered this pretty well, but we'll go over it again, of treating horizontal and vertical components of motion separately, that idea needs to be applied to projectile motion. So when I fire an object like this toy car off of here, two things are going to happen. One, as soon as it leaves the edge of the table, it is going to accelerate towards the floor due to the acceleration due to gravity pulling it down. The other is it's going to move left to right at a constant speed. What will that constant speed be? There's no river here. Noah? Can you give me a number?
4 meters.
It'll be 4 meters per second. And some people get bothered by that. It makes sense with the boat in the river, and here you go, well, geez, won't it slow down? Or, there is no force pushing the car to the left when it's in the air. There is no, so it can't slow down. There is no force pushing the car to the right while it's in the air. So it can't speed up in that direction. The only force that acts on it is downward, and it's gravity. So what is going on here, and I've skipped over some of this, but you know, just to finish this off, in these situations, the horizontal motion will be uniform motion, the vertical motion will be uniform acceleration. Are you with me on that? Horizontal, speed equals distance over time. Vertical, VI, VF, A, D, and T. All right, let's tackle this problem then. How I would like you to solve this type of problem is to make a chart. And the chart is going to have 2 columns. And you're going to put horizontal, and vertical. For the horizontal motion again, and man, I think I've covered this. The horizontal motion will be uniform motion. There's no acceleration left, right. And what that means is in your chart, you're going to populate your chart here with V, D, and T. You know, I could drop the vectors here. I'm certainly not going to put subscripts of X on everything. And over here under vertical, we have VI, VF, A, D, and T. And I don't need the vectors. I'm going to put them. I'm certainly not going to put Y on these things. And now, well, I would rather do it well, explain this to you well, than just brush it away. Do you remember when we first learned the 5 kinematics equations? I don't know if you recall, but the very first lesson we didn't include negatives anywhere. And I told you there was a reason for that, and the reason was in every one of those examples, the direction didn't change, so we don't care about negatives, right? And then we spent a couple days, 2.5 days, looking at problems where the direction does change, like when an object is thrown up or a ball is rolled up a ramp, or even situations where the object is braking to a stop, right? And we said direction is important. When you look at this, the displacement of this car is in fact going to be negative 1.5, right? And the acceleration is negative 9.81. But we don't need to use them because it's all downward. How many of you can appreciate that we don't need negatives here, so why use them? Okay. If you can, then don't put them. I'm going to put them because usually it's the case that most people want to use them because Mr. Way said if the object goes down, it's negative. Okay. So I'm going to put here negative 9.81 meters per second squared, negative 1.5 meters. I'm going to put over here 4 meters per second. And I want you to follow the logic of this, the problem-solving strategy. The question is, what's this? What is this? If you look at the question, it says, how far does it travel horizontally before it strikes the floor? You're asked to find this distance. And that's a horizontal displacement. In our chart, on the horizontal side of things, you're allowed to use this formula. Why? Because it's uniform motion. So, here's the strategy. What are we missing, Joseph, that's preventing us from finding the distance? Time. But what we have to understand is that the time that the time that the car moves horizontally is the same as the time that it moves vertically. So the problem now becomes, how can we find the time with the vertical information? And it's not possible right now. We only know 2 things. What else do we know?
The initial velocity for the car going downward is 0.
Good. And I'm glad you said, Owen, the initial velocity for the car going downward is 0. Because had you said the initial velocity of the car is 0, I would have said, no, it isn't. It's moving at 4 meters per second. But the vertical motion is 0 meters per second to begin with. This is not difficult. Everything that has led up to here, this showing you what happens with the ship that's accelerating in one direction and moving at a constant speed in the other, it all leads up to something that's very simple. You treat horizontal and vertical separately. You have a problem to do here on the vertical side of things with your kinematics equations to find a time, to put the time over here and solve a science 10 problem, a junior high problem. So which formula can we use on the vertical side of things? This d equals 1/2 at squared is a popular one. not always, it will most of the time be used in these. If you want to leave the negatives out, it will work. If you want to put both negatives in, it will work. I'm saying, it's just the way it is, by this point in the course, you'd better be able to put a distance and an acceleration in here and find the time. And if I wanted you to show your work, you certainly could. I'll write something on the board for you. But you certainly don't have to for a multiple choice. This is 2d over a equals t squared. So I can take 2 times that distance divided by the acceleration. How many of you want to put the negatives in? Okay. And I think, if you don't want to and you understand that you don't need to, that's great. I'm going to put the negatives in. I'm going to go 2 times negative 1.5, and then I have to divide by negative 9.81, and I need to take the square root. And I get about 0.553 seconds. Anybody else up for that? Good. Thank you. And again, these 2 times are the same. It's not 2 toy cars. It's 1 toy car doing 2 things at the same time. So I can put that time here. And that's seconds. And now I can do distance equals speed times time. And I want to cover my bases here. You're going to find me more and more in the coming days and weeks not using vector symbols in my formulas. Technically I should have them, but it doesn't really matter in this case. All I need to do is take 4 meters per second times 0.553 seconds. And what we get for an answer is 2.2 meters. Right? I think what I would like to do today, I have to get used to the new bell schedule, is finish the examples, and then tomorrow, we might do a lab tomorrow and practice these problems. So what has turned into, what it was originally like 3 days of this is now going to be 4, between both parts. Now the next question. This is the classic question you're going to see on every exam from now on until the end of Physics 30, including your diploma exam. In this problem we just did, which was a numerical response question, we used 2 physics principles to determine the answer. You have to look at your formula sheet at those list of physics principles. I think I have them here. You did have to use or apply 2 physics principles. Using the numbers on your data sheet, match the physics principles with the order in which they were used. And this is how you will see it on diploma exam and on my exams. Which physics principle did you use first, and which physics principle did you use second? Well, the very first thing we did was we did a calculation over here with d equals 1/2 at squared, and that's an application of accelerated motion. What's going on vertically is accelerated motion. And when you look at your formula sheet, accelerated motion is physics principle number 1. There's more to it. There's this F net is not equal to 0, but we don't need to worry about that. It's accelerated motion. We used physics principle 1 first. Then what we did is we applied speed equals distance over time. Well, that was because it was uniform motion. So we applied physics principle 1 followed by physics principle 0. So you would enter 1, 0 on an exam. Again, and 10 minutes is more than enough time. I'm not going to be rushing through this next example. We can do this next example. In fact, I think maybe you could probably do it on your own. It's a little bit different, I admit, because there's no picture. But a stunt person drives off of a cliff that is 75 meters above the water, and they land 132 meters from the base of the cliff. What does this look like? Vroom. Off the cliff. Some craggy cliff, water. And what's going to happen is it's going to land 132 meters from the base of the cliff. Is that right? How high is the cliff? Whoops. $75, 132, sploosh, right? I wanted to have it a reasonable distance, that if that's 75, if that's 132. So what we have going on here, that looks like a bug of some kind. What we have going on is horizontal motion that is uniform, and we also have vertical motion that is accelerated. So if you were asked to determine, what are we asked to determine? The speed. How fast is this car moving to begin with? I hope you would agree, whatever speed it's traveling at, if it went faster, it would travel further than 132 meters. And if it were traveling slower, it would land closer than 132 meters from the base of the cliff. There's a physical connection there. Well, we're going to set this up with horizontal motion. This time I'm going to call it uniform motion. And the vertical motion is uniform acceleration. Could you call the vertical motion just accelerated motion? Sure, of course. Bottom line is, this is all about x, and this is all about y. So the part that's about x, we can talk about things like speed, distance, and time. The part that talks about y, we can use things like vi, vf, a, d, and t. Yeah. Because some of you will want to use negatives for the acceleration and the displacement, I'm going to put vectors there. I'm not going to put vectors in the left-hand column because that's just speed equals distance over time. Let's put the information in that we have. 85 meters for a height of a cliff? 75. That means the displacement of the car is going to be negative 75 meters. And again, the negatives are not needed here because the car doesn't change direction. It's always moving downward and to the right. The acceleration due to gravity is negative 9.81 meters per second squared. VI is 0. I think that's, is the initial velocity of the car 0? No, the initial velocity is 4 meters per second east. But the initial vertical velocity is 0. Right? And by the way, that initial velocity of 4 meters per second east is the velocity east all the time because it's not accelerating. Oh, I'm back on the other question, aren't I? My mistake. We are asked to determine this. Okay, good. And we know this is 132 meters. All right. So if we want to determine V, and speed over here is speed equals distance over time, then we need to know the time. Well, it's the same kind of problem we had before. By the way, you're not always going to do this calculation first. Sometimes you might have this calculation and then do something over here. Maybe if I'm asking you how far it falls. But we can certainly do this. This is 1/2 AT squared equals displacement. I'm going to give you a minute to put your displacement and your acceleration in there and figure out what you get for a time. I'm just going to guess 3.7. 3.9? You can carry more decimals, of course, on your calculator. Now what we can do is we can say that that time of 3.9 seconds is the same These are the same. And we've turned this, really, we've gone from quite a complicated problem. Listen, we've gone from a very complicated problem, one that was new to you prior to today, to a problem you could solve last week, to a problem you can solve in grade 8. I think if I told a student that an object traveled 132 meters in 3.9 seconds, how fast is it moving? I said that to a grade 8 student, should be able to figure it out. And that's really my philosophy in teaching. You try to turn something from a higher level into something simpler and simpler and simpler until you get the answer. I'm going to do this on my calculator so we all have a number to look at. What do I have to do? 2 times 75 is 150 divided by 9.81. I'm not using the negatives here. Take the square root. 3.91 seconds. I have to take 132 meters divided by that answer. And I get about 34 meters per second. How many significant figures do we want? 3. So 33.8. Yep. So the answer to this numerical question of how fast is it moving is 33.8 meters per second. I don't know, over 100 kilometers per hour. And which physics principles are used and what was the order in which you used them? Well, in this question, just like the previous one, you used accelerated motion followed by uniform motion, but it's not always going to be that way. I could have given you the speed of the car and not the height of the cliff and asked you to find the height of the cliff. Tomorrow is going to be a day where we will do a demo. We might do a lab tomorrow. I normally do the lab with objects that are launched at an angle, and we will do that. But I'll see if I can come up with a basic lab we can do where we launch objects this way. Okay. I have to really rack my brain over that. But we are going to be working mostly on... do you have another example on yours? That was it, right? Oh, there's a few more. Okay. So we might do the remaining examples tomorrow as well. We'll see. If you want, if you feel up for it, you can maybe just... so this is the next example? Yeah. I wouldn't touch example 5. If you want to, you can try number 6 for tomorrow. We're going to be doing 6 together. Number 5 is relying on a demo that we're going to do. So tomorrow we'll come in, we'll do a demo, we'll do example 5, and then we'll finish the examples and practice with the other stuff. We might get to a lab tomorrow, we might not. When the bell rings, have a wonderful day, you guys. I hope that made sense. Again, I'm recording this, so if you need to go back and look at it again, do so.